Okay, let's go ahead and get started. So last time we covered fundamental theorem of calculus part 1, where we had the area accumulating function, and we started substitution. And now we're going to finish working on substitution and perhaps start looking at the area between curves. The setup is that there's an inside function, or in most cases, and then the derivative of that function shows up somewhere in the rest of the integrand. We call it the outside. Your task is to let u be g of x. U is just a dummy variable, it can be anything. So we let u be g of x. When you take the derivative of that, you get basically, if not exactly the rest of the integrand, maybe just some constant multiple times the integrand. And the point is to turn it to a simpler integral. So we worked the example rather quickly. We didn't finish it, where we had x squared times the square root of 1 plus x cubed. And it's not exactly true that the derivative of 1 plus x cubed is exactly x squared. We found out that if we let u be the inside, 1 plus x cubed, the derivative of it is 3x squared dx. It's a process of substitution. We have to figure out what to substitute for, and what's under the root is what we substitute u for. And the stuff that's on the outside needs to be substituted for as well. And so what we do is, when we write the derivative of u, we write it as like a differential. And then it's a matter of trying to solve for what's left over. There's x squared in dx. We have to solve for that. We have 3 times that. Basically, we just need to divide by 3. And so 1/3 of du is going to take the place of that x squared dx. And the integrand just becomes root of u times 1/3 du. And it is simpler. The whole point was that we get to an integral that we can just use the power rule in reverse, or just somehow quickly find the antiderivative of. And we make the root of half as an exponent. We use the power rule in reverse, where we add 1 to the exponent and divide by exactly the same thing. So that's how we end up with u to the 3/2. But instead of dividing by 3/2, we multiply by 2/3. This extra factor of 1/3 that was there gets carried along for a grand total of 2/9 of u to the 3/2. The whole purpose was to be able to find the antiderivative of the original function in x. And so we have to substitute back and write the antiderivative in terms of x, replacing the u with what it was in terms of x, 1 plus x cubed. And that's where we stopped at. Now this actually is more than just a find the antiderivative question. This is find the area under the curve question. And so it's hard to see now, but the limits of integration are 0 and 2. Yeah, 0 and 2. So we need to evaluate this antiderivative at 2, and then subtract from that this antiderivative evaluated at 0. Okay, so the answer to this question, the integral of 0 to 2, x squared times the square root of 1 plus x cubed. Sorry, let me put that squared there so people don't get confused. We found that the antiderivative is 2/9, 1 plus x cubed to the 3/2. And now we're going to evaluate that at 2, and also evaluate it at 0. So we take the 2/9. You'll find it helpful to pull out a constant. If you have a constant involved in your antiderivative, multiplied by your entire antiderivative, you'll find it useful to pull that constant out. Instead of putting the 2/9 in both of the parts, the antiderivative evaluated at 2 and the antiderivative evaluated at 0, you'll find it helpful to pull the 2/9 out. And so we have 1 plus 2 cubed to the 3/2 minus 1 plus 0 to the 3/2. Okay. Pull the 2/9 out. 2 cubed is 8. 8 plus 1 is 9. 9 to the 3/2 is the square root of 9 and then cubed. Okay, so it's 3 cubed is 27. And 1 to the 3/2 is 1. So we get 27 minus 1, but don't forget the 2/9 is there. So the area under this function from 0 to 2 is 2/9 times 26. (52/9) is the answer. Questions about that? Yes?
What happens if the du is off by more than a constant factor?
Then you probably can't use U substitution. U substitution is useful when you take the derivative of the inside and you're off by at least a constant, or you're exactly the derivative of that u is exactly the outside or off by a constant. We have other techniques, but we just don't learn them in this class. You have to go to 104 to learn how to use other techniques when things fail, basically. All right. Now, there's another way to do it without having to switch back into x's. The whole substitution is exactly the same, but when it comes time to work this integral, you change the limits of integration. So some people prefer not to have to go back into x's. It's a personal choice. It's totally up to you. If you don't want to go back into x's, then you need to change your x limits into u limits. Well, how do you do that? You take these x limits of integration and you plug them into the substitution to get what the u limits of integration are. And so the substitution is exactly the same, but at this point you don't have to worry about going back into x and plugging in the original numbers, and you can just evaluate the problem from here. Some people prefer this way. So actually the integration of u is exactly the same. You still get the 2/9. I'm sorry, this animation is out of order. But now, instead of plugging back in for x's, you're plugging a 9 in for u and a 1 in for u. And you get the same thing. Some people think this is cleaner. They rather do this. Requires you to do a limit switch. Sometimes that limit switch will get you in trouble because by the way that the u would work, sometimes it's possible to have the upper limit be smaller than the lower limit, and you might miss that. And so you want to just be careful when you do a limit switch. Let's look at another example. Cosecant squared x times the cotangent of x from pi over 6 to pi over 4. So this requires you to know derivative of trig functions that are not your standard sine, cosine, tangent, the reciprocal guys. What's cotangent's derivative? Negative cosecant squared. So you essentially have cotangent's derivative as the rest of it. There's really not an inside and an outside here, but you just have to know that cotangent's derivative is exactly cosecant squared with a negative on it. So with that in mind, then we're going to let u be cotangent, and then the rest of it is essentially the derivative of that. This animation is out of order. Let me just abandon the animation. So I can stop this now. So we let u equal cotangent of x. Du is negative cosecant squared of x dx. As far as substitution goes, we have to substitute for cotangent of x. That's just going to be u. And we have to substitute for cosecant squared of x dx. So we just multiply this by -1 or divide by -1. And it's going to be the opposite of du that takes the place of that cosecant squared. Of x dx. The opposite of du would take the place of that. And so this integral is much simpler. You get u times a -1 du. That's what these guys were replaced by. This -1 du. All right, pull the constants out. So we're talking about integrating u du. What function has u as its derivative? Power rule in reverse. Think about it as u to the 1, just u squared over 2. Okay, we have to put a negative on there. That's it. That's your antiderivative. Now it's your choice. Do you switch the limits of integration, or do you go back and use the original x values? I'm going to go back and use the original x values. I just want you to see in the last example how you could do it with the limit switch. And so go back into x. So what was u? U was the cotangent of x. Okay, so the whole purpose of all of this, I like to think about it as sort of side work. It was a tool to help me figure out that the antiderivative of my original function is exactly -1/2 the cotangent of x. I'm going to write it like this, quantity squared. And I have to, this line and then the limits there, it's just a statement that the next thing I'm going to do is plug in the upper limit and then subtract from that what I get by plugging in the lower limit. That line there is a statement that says I'm done with integration now. I found my antiderivative. Now I'm going to use the fundamental theorem of calculus and plug in. Questions on that substitution? Pretty straightforward. The hard part comes in evaluating cotan. I don't know values of cotangent. I hardly know values of tangent, but I know values of sine and cosine. So it might be beneficial to go into sine and cosine. Let's do that. What is cotangent in terms of sine and cosine? It's the cosine of x divided by the sine of x. Let's do that instead. So let's have the -1/2 just come out front, and let's deal with the cosine of x divided by the sine of x. And we have to plug in a pi over 4 and plug in a pi over 6. Okay. Well, with pi over 4, they're going to be the same, right? Cosine is the same as sine. And we have to square that. Sorry. So with pi over 4, they're exactly the same, right? Cosine of pi over 4, sine of pi over 4, they're both 1. I mean, they're both root 2 over 2. So when we divide, we get 1. So we're going to get -1/2, and then we're going to get 1 from plugging in pi over 4. Now let's plug in pi over 6. What is the cosine of pi over 6 divided by the sine of pi over 6? Squared. With cosine, for pi over 6 at least, for 30 degrees, cosine is the larger one. So that's the root 3 over 2. And then we divide that by 1/2. What does that simplify to be? Just root 3, right? Okay, but then you square that, so you get a 3. So you get 1 minus 3 with a -1/2 constant pulled out. It's really helpful that you pull the 1/2 out.
the final answer? 1. Very good. It's a negative half of negative 2. Okay. Questions? Yes. I subbed back in. U is equal to cotan. My antiderivative is negative half of u squared. I mean negative half of u squared was my antiderivative when it was in terms of u. I replace u with cotan, so I have negative half of cotan squared. So maybe your issue is not understanding how the substitution worked. That's where that came from. It came from the substitution. Yeah. More questions? Yes.
What happened to du?
What happened to du? After finding the antiderivative, it kind of falls out. Du is just basically part of this integration symbol. Whenever you have the integration symbol, you need the d of whatever variable you're integrating with respect to. And so, yes, it was necessary to do my substitution, but once I found my antiderivative, I drop it. Like I don't continue to write du, just like I don't continue to write the integration symbol. They go together. They're paired together. Never write an integration symbol without a du. I'll take off point. How about the sine of 3 pi x? From 0 to 1. So, what would you consider the inside function? 3 pi x. Very good. Let u be that. What is the derivative of that? 3 pi. We'll put the dx on the end. Okay, now if you look at this, we really just have, like, sine isn't anything itself. It's part of the sine of the 3 pi x. So the only other thing that's left out there is the dx. That's why the dx is important to be there. You can't just disregard it. So we have to sub for dx. We already know how to sub for sine of 3 pi x. We're just going to call that sine of u. So how are we going to get what dx is? Well, we have a statement here about dx, involving dx, but it has this extra constant on here. So we divide by 3 pi. And it says that 1 over 3 pi times du is going to take the place of that dx. In essence, you just have to factor in an extra 1 over 3 pi. In general, if you're trying to integrate sine of kx, where k is a constant, you have to have an extra 1 over k outside. And then let's see what happens after that. What function has sine of u as its derivative? Negative cosine. So we get the negative 1 over 3 pi times the cosine of u. All right, technically plus a constant. Well, so that's it. 1 over k negative cosine of that same kx. Go back and put back in what u is. All of this here side work was for us to figure out that the original problem as posed to us, we use that as a tool. This is the substitution was a tool for us so that we know exactly what the antiderivative is. The antiderivative is exactly negative 1 over 3 pi times the cosine of that 3 pi x. You sub back in. Replace u by what it was. You don't have to do it this way. Like, you can do it intuitively if you want. I'm just trying to show you how the mechanics of it works. Okay? Your job was to find the antiderivative. You needed this tool to help you, but now you have it, so move on. Use the fundamental theorem of calculus and plug in 1 and subtract from that what you get when you plug in 0. To make your life easier, that constant that's out front, don't put it in both of them. Just pull it outside. So let's have it as negative 1 over 3 pi, and then we have the cosine of 3 pi when we plug a 1 in, and the cosine of 0 when we plug a 0 in. What's the cosine of 3 pi? Same as cosine of pi, negative 1. And the cosine of 0 is 1. They don't cancel out, though. You get negative 2. So the final answer is 2 over 3 pi. In general, now, this is like cheat sheet material. If you have a k, just remember that there's going to be a 1 over k. If that k is a fraction itself, then 1 over that fraction is going to be, you know, if you're trying to integrate sine of x over 2. Using this, we're going to see that it's just negative 2 cosine of x over 2. Right? K is a half. 1 over 1 half is 2. So when you do that reciprocal, it's going to be just multiplied by. So in general, you don't have to. You can skip the. Now that you know this, you can skip the u sub, because the whole point is to be able to get that antiderivative. And so you can use these formulas to help you get the antiderivative. Maybe you should put that on your cheat sheet, save you some time, and you wouldn't have to go through the antiderivative. I mean the substitution. You can jump right to what the antiderivative is. Undo that. How about now? What would you let u equal? Square root of x plus 1? Sounds good. Because its derivative is 1 over 2 times the square root of x. And you have 1 over the square root of x. Don't just let it be root x. Take the whole thing. Root x plus 1, so you can take the whole thing and have it to the second power. So go take the derivative of it. You don't have exactly that. You have 1 over root x dx, so you need to get rid of that 2, so multiply by 2. That's what's going to replace the 1 over root x dx. Okay? So what's going to happen is the u squared is in the denominator, And then all of this, 1 over root dx, gets replaced by twice du. And we need to find that antiderivative. Think of it as 2 times the u to the negative 2. What's the antiderivative of u to the negative 2? U to the negative 1 over negative 1. Okay, so we'll get negative 2 over u, simplifying that. Okay, so all of this was side work to help us figure out that, oh wait, you know something different about this? We haven't seen this yet. This symbol has no, I should have introduced that earlier. There's no limits of integration on there. I should have said that, sorry. Side note, integration symbol f of x dx with no limits of integration. What does that mean? You're not finding an area. Okay? When there's limits of integration, that's finding an area. Okay? This is called an indefinite integral. The other one was called a definite integral. This is called an indefinite integral. They just want you to find the antiderivative, that's all. It's just a glorious way to say, go get the antiderivative of this. Okay? So without the limits of integration, they just want you to find the antiderivative. We could have written the questions in 4.8 using this symbol, but they just didn't introduce the symbol back then. And so this is really just a 4.8 question. Go find the antiderivative of this, but we'll have to use substitution to get it. We did the substitution. We have the antiderivative. It's just in the wrong variable. It's in u. So translate back and put it back in terms of x, and you're done. The antiderivative is exactly, if you want to call it capital F of x, you can. It's exactly negative 2 over the root x plus 1. The 1 is not underneath the root. I'm surprised by so many people that want to throw the 1 under the root. When I have questions like this on my exam, so many people just want to extend that root, and it's not. It's not in there. It stops at the x. Okay? Plus the constant. So adding the c is necessary because it was back then. We're just finding the antiderivative now. We're not finding the area under the curve. Questions? How did we get to negative 2 over u? Where did it come from? What was right before it? U to negative 1 is 1 over u. Negative 1 turned the 2 into a negative 2.
I mean, you bring the u down and then, oh, you're dividing. You're still dividing the negative 1.
Multiplying, dividing, it's all the same with negative 1. Doesn't matter where you put it at. Let's do some with e's and logs. 6e to the 3x from 0 to log 2. What would you consider the inside function? Just the 3x. So if you let u be equal to 3x, the derivative is 3. All right, we have 6. So this is what we want to get, 6 dx. This is what we have, 3 dx. How can we turn 3 dx into 6 dx? Multiply by 2. Twice du will be 6 dx. All right, we had 3 dx, we wanted 6 dx, so we double. All right, so that's what's going to take the place of 6 dx. So the substitution becomes e to the u, and then times 6 times 2 du. Or 2 times e to the u in the integrand. What's the antiderivative of e to the u? E to the u. Very good. All right, you're done. You can do a limit switch if you want. Let's go ahead and just go back into our original variables. All of that was to help us figure out that when you pose the question like this, I needed to know what the antiderivative is, and I just went and found it. I just got to return the variables that I had it in, which is x, and so I replaced the u with x, and now I just have to plug in my limits of integration, 0, and the natural log of 2. Okay, this was all side work to help me figure out what the antiderivative of that function was. You might have been able to do it mentally. If you can do that, that's fine. You know you're going to need a 3, but then you have to divide by that 3. Now, you can do that. In general, right? You can skip the u substitution just like we did with the sign. If you have e to the kx, essentially you're going to have to divide by k. This extra 6 here was divide by 6, that's how it became a 2. I mean, divide by 3, that's how it became a 2. So anyway, plug in log 2, what do you get? Pull the 2 out. I don't recommend leaving the 2 in. Just focus on the e. I have e to the 3 log 2 minus e to the 0. Most people skip that step. I recommend writing it out. Of course you're going to evaluate. Of course you're going to simplify it, but it helps to write it out. Sometimes you see 0 as a lower limit, and you automatically assume that it gives you 0, but it doesn't always. Here's the case where it doesn't. E to 0 is 1. What about e to the 3 log 2? Be careful. Yeah, so don't do this. Don't just cancel the e and the log. It doesn't work that way. They do cancel, but you have to do something first. Okay? It doesn't work that you can just cancel this. Don't do that. Don't call it 6. You got to get rid of the 3 first. Get rid of the 3 how? By bringing it up as the exponent on 2. 3 log 2 is the log of 2 cubed. Right? Don't let this algebra get in your way. It's the log of 8. So what this really is e to the log of 8, and then you could cancel. It's an 8 in disguise. It's a fancy way to say 8. 8 minus 1 is 7. 7 times 2, 14. That's your answer. How about this one? 1 over 3x plus 2 from 0 to 2. What do we do? Yes? It looks like an ln. Right? 1 over u, if it was a u, it'd be an ln. But you can't just say it's the ln of 3x plus 2. Okay? There'll be an extra factor in there that you need to account for. Just like with e to the kx, there's an extra 1 over k. With this, there's going to be an extra 1 over 3. We'll do the u substitution. Let u be the entire denominator, so you're just doing 1 over u. But then there's an extra factor of 3 that comes in because the derivative, the chain rule, is going to bring this 3 in, and you have to undo that 3. You have to divide by 3. So 1/3 of du is going to take the place of that dx. Don't think that dx is insignificant. It is part of the substitution. So it is a natural log, definitely, but there's an extra factor of 1/3 that I don't want you to forget about. And technically there's absolute values around it, but since we're considering x's between 0 and 2, it doesn't flip negative. Technically the antiderivative of 1 over u is the natural log of the absolute value of u. To allow for negatives, and then you throw the absolute value around them, and it allows you to be able to plug it into log. That's a technicality, but for us it's not going to matter because we have zeros and 2s. It doesn't turn negative. So the antiderivative is 1/3 the natural log of 3x plus 2. Let me just use parentheses. Okay. That was our job. Go get the antiderivative. Now we have it. The original question, let me just rewrite it. And all of that above was to help us know that the antiderivative is 1/3 the natural log of 3x plus 2. Now let's plug in a 0 and plug in a 2. Plug in a 2 first, though. What happens when you plug a 2 in? What is 3 times 2 plus 2? So we have the log of 8. Okay, what are you going to do with that 1/3? I recommend leaving it outside, like we've been doing these other ones. So we have 8. The log of 8. Very good. What happens when you put a 0 in? The log of 2. Very good. Great. Log of 8 minus log of 2. You look at the answers and you don't see that. They have you combining these logs into one log with division. 8 over 2 is 4. So it's 1/3 the natural log of 4. Now had it been a perfect cube, we might even bring that part up. But that should be the answer that's in the multiple choice or in the back of the book. Sometimes it doesn't work out so nice. And so we have to have a hard example. That's what the next one is. Question, yes? Why did I divide by 3? Just look at what we have to sub for. We have to sub for dx. And you have 3dx. So divide by 3. All right, so we need a hard example. And right before we do that, let me just give you some advice here on this last slide. We'll go back to this previous slide. Let me give you some advice on this last slide. Here's what's going to happen. That section about area between curves section, I guess it's really part of 5.6. It's weird. This book does substitution in 2 different sections, 5.5 and 5.6. And then also in 5.6 it does area between curves. What will happen is basically we'll do that on Friday, the last day of class. It won't be on this exam. 5.6 won't. Area between curves won't. And so, but it will possibly show up on the final, so we'll do it on Friday. That'll be the last section we cover. On Monday, we review. Wednesday's our exam. Friday, we'll cover that 5.6. And I'll have skeleton notes up for you for that. This is just what we need to know for this exam, though, this last little bit here. This is more properties. This should have been in the properties section, but for some reason, our book didn't cover it till now. An even and an odd function. We talked about them before. An even function is one that's symmetric with respect to the y-axis, and an odd function is one that's symmetric with respect to the origin. Okay, even is y-axis symmetry, and odd is origin symmetry. Okay. So think about what you're doing. If you're integrating over an interval that is symmetric around 0 from minus a to a, think about if you were integrating a function that's even. Okay, look at the picture. Here's a function, a graph of a function that's even, and I'm supposed to be integrating from minus a to a. Because of the symmetry of it, I don't have to go from minus a to a. I can go from 0 to a and double. I'd much rather have 0 as a lower limit. Plugging in 0 is much more desirable than plugging in minus a. So you can trade it in. Instead of integrating from minus a to a, you can double integrating from 0 to a when it's even. Okay. What about when it's odd? Oh, there's an example there. An example of an even function is there. And don't worry about it. You can look at how it works out. When it's odd, the answer is 0. Look at the graph. Here's a graph of a function that's odd. Remember, the area below the x-axis like this is negative, and the area above is positive, and they're symmetric. So this negative area will cancel the positive area. And so that's a gift. If you're given an odd function and asked to integrate it from some minus a to a, you can just report the answer as 0. It's up to you to recognize if it's odd or not, though. An odd function, polynomial-wise, is a function that has only odd exponents. An even function, polynomial-wise, is a function that has even exponents and possibly a constant. An even trig function is cosine. An odd trig function is sine. So you can combine these together. An even plus an even is even. An odd plus an odd is odd. And you can look at those examples. I want to make sure we get to this hard U-sub example. Any questions on this slide, though? So take advantage of that. Whenever you see, think about whenever you see minus a to a, some number on the lower limit as a negative and on the upper limit as a positive, then some alarms should go off, and you should check and see what's on the inside. If it's even or odd, that's a gift, especially if it's odd. I just have you state that it's odd and tell me that it's 0, and you're done. You don't have to do any integration. Okay, let's get back to this hard U-sub example. Question? Oh, you have to know the definition of even and odd in chapter 1. Freak out. Okay, so here's a hard U-sub. I don't know if we can do it in 5 minutes. At least get a start on it. The derivative of the inside is not the outside at all. This is like the derivative of x minus 1 is 1. But you can still do a U-sub on this. When the power inside is 1 higher than the power outside, that's when U-sub works nice, and that's what we've been doing. When the power inside is exactly the same as the outside, you can still do U-sub. It's just a little bit of work. I'm still going to let u be x minus 1, definitely, because that's the inside function. And so, when the powers match like this, I have 3 parts. They're in 3 different colors. I don't know if you can tell about the colors, but anyway, the blue is x minus 1, the red is x, and then there's the dx. So I let u be x minus 1, and the derivative is definitely, the derivative of that is 1, dx. So the dx will be replaced by du. The x minus 1 will be replaced by the u. Now, to replace the x, I have to resort to taking this substitution and solving it for x. That's the only way I can replace the x. Only do this if these powers match like this. Okay? This is the only way this is going to work. If the powers match inside and outside. Okay, so then x is going to be replaced by u plus 1. Here's a limit switch. Let's see. Let's not do the limit switch. So x is replaced by u plus 1. X minus 1 is replaced by u. But don't forget it's under a root. And then dx is replaced by du. Why is that better? Why is that doable? Why is that good? We can find the integral of this. It doesn't look like it right now, but with a little bit of algebra, we can simplify it. Okay, there's no quotient rule in reverse. But if we have a bunch of individual terms that we can do the power rule in reverse on, then that would be good. When you have multiple terms in the numerator but a single term in the denominator, you can split it up. And so that's what we're going to do. We're going to call it u over root u and 1 over root u. Because that gives us two individual terms that we can do the power rule in reverse on. U over root u simplifies to be root u. And that's u to the half. This 1 over root u is u to the negative half. I haven't integrated. Let me go put the integral symbol back on. And now I'm about to integrate because I can just quickly do the power rule in reverse. So this substitution was involved, but it got it to its place where we can find the antiderivative, and then later we can go back. Antiderivative of u to the half, u to the 3 halves, divided by 3 halves. Antiderivative of u to the negative half, u to the 1 half, divided by 1 half. We don't really divide by fractions, we multiply by reciprocals. And so, we're talking about 2/3 of u to the 3 halves plus 2 root u. Let's go ahead and put it back as a root. That's the antiderivative. It took a lot of work, but that's the antiderivative in a wrong variable. It's in u. If you want, you can do a limit switch. We can say, well, let's get the new u's, and let's just plug in the new u's. Just don't do the forbidden thing of plugging in these x numbers in the u's. Don't do that. So it's your choice. We can do a limit switch, or we can go back to x's. Let's go back to x's. So we have 2/3 of x minus 1 to the 3 halves, and 2 times the square root of x minus 1. Now let's go plug in a 2 and a 5. Okay, you finish that out. You'll see it on the slides. Time is up. Have a good weekend. I'll see you on Monday. We'll review. Come with lots of questions on Monday. Inside means like raised to a power as an exponent. You know what I mean? Yeah. Yeah, that's when we do those e to log x questions, that's 7.5. Yeah. Okay? All right.